The last class, we looked at the classification of boundary value problems into 3 categories. We said that category A was basically all those problems that are smooth, for which the solution is you can actually expand in Taylor series. So those problems are nicely behaved, and then you can get the best convergence rate. So when problems are smooth, and this is what you see in the projects, you get to obtain optimal convergence rates, basically. Now, problems in category B were those of contained singularities, but remember that we defined those singularities to be in a portion of the domain that had 0 measure. And if you remember, that was a point in 1D, or a point and a line in 2D, or a point and a line or a surface in 3D. So those are basically regions in your domain that have 0 volume. And the convergence rate goes down, but you can still get really nice convergence. And of course, problems in category C are not in these other 2. And what we're going to do today is we're going to look really at the theory behind these convergence rates, right? We're going to classify really, we're going to look at p-FEM, at h-FEM, and we're going to see what are the real convergence rates that you would expect to see when you're solving one of these problems. So for that, we're going to get into what is called a priori error estimates. Okay. And there are basically 2 types of error estimates. There are the algebraic error estimates that basically tell you that your convergence rate is constant. As you refine your mesh, you're going to get the same convergence rate. That means that if your energy convergence rate is of the order of 1, if you keep refining your mesh, right, you should pretty much say that convergence rate remains unchanged. And so it really doesn't matter. You know how your error is going to decrease with mesh refinement, right? Those are algebraic convergence rates. Then you have the exponential convergence rates, which are actually much nicer because you can actually show that your error goes faster to 0, which basically means that your convergence rate improves as you are refining the mesh, or as you are increasing the number of degrees of freedom. So how does look like? Well, in h-FEM, so I'm going to be dealing with the energy space again. So its error in energy norm is going to be equal to C1 h to a power of beta h, and beta h is basically my convergence rate times the norm of the exact solution. And in this equation, C1, this is a constant that is independent of u, and h. H, who can tell me what h may mean here?
Mesh size.
Mesh size, but minimum or maximum mesh size? Yeah. Again, your error is going to be controlled by the weak link in your problem, and that is the element of maximum size. And beta h here is our rate of convergence. And it's dependent on p and u. So that is the estimate for h-FEM, and this is actually quite sharp. We're going to look at that. For very small mesh size, you can really expect that is very, very accurate estimate. So when we are dealing with convergence rates in finite element analysis, we're always talking about terminal convergence. So you never really take a look at the coarser mesh that you have, but actually you always take a look at the last two simulations that you had, right? Well, if your energy rate, if your error in the energy norm is decreasing in an algebraic way, so your rate is not supposed to change, yeah, so you can take basically any point, any simulation that you took, and you're going to get the same rate. But normally, when we get convergence rates, we're really talking about terminal convergence. And this is because when you're dealing with very coarse meshes, you may have other issues, boundary conditions, and so forth, okay? Maybe your course was so meshed, we discussed a little bit about it, that your body force was not integrated properly. These are the sort of things. So we're always looking at terminal convergence, all right? For p-FEM, that estimate or algebraic convergence rate looks like this. And then this p, C2 of course is another constant. Then beta p is your rate of convergence for p-FEM. And this p is what? Order, but minimum or maximum?
Maximum.
Minimum. Very good. Okay. So those are the algebraic rates. Now, exponential rates which you can obtain. Can you obtain exponential rates of convergence with h-FEM? No. So you can only obtain this with p-FEM or with, what is the other? Yes. And it looks like this. Right? So you have 1 over e to the power of gamma n to the power of theta. So here we have also some other constants. So gamma, theta are constants that depend on the solution, and n is, what is n? Where? U minus UH, that is the norm in the energy norm, is less than or equal to C divided by the exp, which is e to the power of gamma n to the power of theta. Is it my handwriting? Yeah, okay. Sorry, I cannot do much about that. I should take a calligraphy course. Anyways, n is the number of, so before we were dealing with h and with p, and now we're dealing with n. What is n? Almost. Number of? No. Yes. Okay, so far this doesn't tell us much. It's basically an equation that is saying, okay, you know, how our error, because you see here we have u is our exact solution and UH is our approximate solution. So this is telling us a little bit how our error, because u minus UH is our error, right? How that is decreasing. So let's take, for example, the first one of these algebraic. Let's see how that looks like when you actually plot that. Okay, so let's define our error, and it's going to be our relative error. So I'm just going to combine these two here, and I'm going to define this E as just U minus UH divided by U. This is the relative error in the energy norm. Okay. So now if I take, I'm gonna take this equation here, and I'm gonna take the natural logarithm to both sides. Okay. I just want to plot that function to see how it looks like. So on one side, we're going to have the logarithm of our error, we just defined, is less than or equal to the natural logarithm of C1 plus beta h, the natural logarithm of h. And now I have an equation that if you can actually plot this, so I'm gonna do here h. In fact, I am interested in log of h, right? This is a log-log plot, which is what you should be trying to create in your projects. And this is the log of the error in the energy norm, or more precisely, the relative error in the energy norm. What this is basically saying is that you have a line. And what is the slope of that line? So in log-log space, this is the equation of a line, right? So you can see, for example, this is going to be your independent variable x. This is going to be your ordinate y, right? So what is the slope of that line? Beta h. So I'm going to draw. That is my line. And now I want to draw so this is the type of plots that you should be getting when you are plotting your log-log error in the project. Who has done this already? Only 2, 3, 4? How many? How many more? Who has done log-log plots? 5, 6, 7, 8, okay, a few. Okay, so that is what you should be getting for h-FEM. And in fact, for a linear approximation, that beta h should be equal to 1. All right? Okay. The second one is very similar. So let's try to number this. Let's say this is 1 here, 2, and 3. You can see that 2 basically is the same one, but now p to the power of beta h is in the denominator. So when I take the natural log of that, it's going to have a negative convergence rate, right? I'm taking the natural log of the ratio. Well, let's do it. Let's do it so that you have it. So let's call this 1. But I'm gonna go really quick on this. So and so what you would expect is that if you do the same, you get something that looks like that. Why a circle? So now this guy here is your beta p. But more interesting is the one that is exponential rate. So now we're going to be looking at this guy here.
Excuse me, what I have?
Yeah.
The x-axis on the previous one should also say relativity.
Ah, yes, of course. Thank you so much. Yeah. So now we're going to look at the exponential rate. So if you take the natural log, so look what's happening here. We're going to be analyzing this equation. So you see that I am actually interested in how the error is going to be decreased with the number of degrees of freedom, right? So if I take the log once to that, let's see what we get. This is 1. That is still not very useful, because what you see here is that depending on the number of degrees of freedom, so if I really want to see the behavior of this convergence as I increase the number of degrees of freedom, well, there is one exponent there that is basically going to improve the reduction of the error. So if you take again the natural logarithm to that, so if I do this, then what you get is that you get this minus the natural log of gamma minus theta natural log of n. And you can basically take all of this and say, well, this is some constant. Let's call it C3, right? And now, when you plot this, right, you see that now I have a new slope that is theta there, right? So if I do the plot, of course I have to plot on the ordinates. I don't have the natural log of the error, but the natural log of the natural log of the error, right? And in abscissas I have the natural log of n, and now I get again a line which has negative slope, and the rate of convergence there, let's say, is theta. So basically what this is saying, if you really just try to obtain just the natural log of the error, what you're going to see is that your convergence rate is going to vanish like that. It's going to be really going faster to 0. This is called exponential convergence rate, and you can actually really see that it's exponential, because if you really take the natural log of that equation again and you plot it, you should really see a straight line, and the slope is theta. And there are of course some theory behind what is the value that I should expect to see in that theta, and we are going to look at that too. So if we put all of this together into a table, right, we're going to just make a table where we're going to say, well, what is the rate that I would expect to see if I solve a problem, let's say in 2 dimensions and p order of 3, and you check the table and say, okay, I should be getting this, and then you go and check. All right. So if we put here category, and we saw, well, there are 3 main categories. We said A, B, and C. And we have H, P, and HP. And this is my version, right? Either the H version of p-FEM, or P version of FEM, or HP. Well, it turns out that if we're just looking at smooth problems, which are in category A, right, you are expected to see in h-FEM an algebraic convergence. And your beta H is actually equal to P, the polynomial order that you're using in the approximation. So if you are solving for a linear problem, if you're solving for a problem and you're using linear elements, your convergence rate should be 1. If you're using quadratic Lagrange elements, then your convergence rate in the energy norm, remember that everything we're talking about is in the energy norm, then your convergence rate should be equal to 2, and so forth. Okay? Now, for p-FEM, what we saw is that we get what type of convergence for smooth problems? Who can tell me? Yeah, exponential convergence. And that theta constant you would expect to be greater than or equal than 1 over d, and d is the dimensionality of the problem. So for 2D problems, that is 1/2. For 3D is 1 over 3. And that is, of course, how you are expected to see the error reduce. If you do that, remember, we're basically plotting the natural logarithm of the natural logarithm of the relative error in energy norm versus the number or the natural logarithm of the number of degrees of freedom. So if you do that, you get a straight line, and the slope should be greater than or equal to 1 over d. And if you look at the chapter that I posted in the Nota Bene, which, by the way, I really appreciate all your input. All of that is super nice feedback I get. So I really appreciate your reading and your commenting, and you're being very critical. Hey, this is wrong. Really appreciate it. But if you look at the examples that I put in the p-FEM chapter, I actually do this, and there are two problems where you can see that there is a straight line when you really take the log twice to the error. All right? So in HP, you also get the same as expected, of course. And of course, it cannot get, because it's already smooth, so our solutions are already very good. So you cannot get better than 1 over d. Now, for category B, things get a bit trickier, because then you really have to look at how the solution behaves. And remember, we placed problems in category B, those who have some sort of singularity, for example. Okay? So h-FEM is going to get, again, algebraic convergence. And beta h is going to be determined by either the minimum of p or k minus 1, and I will discuss what k is, or p. And p, we're talking about optimal meshes. I'm going to have space here. Okay, so then now we have a thing here, because you say, well, what is the minimum of p and k minus 1? K is the regularity of the solution. So when we're talking about regularity, we're really talking about how smooth our exact solution is. So if our solution is not very smooth, right, you basically don't have a high order of k. So k refers to the Hilbert space order where your solution lives. Okay, very abstract. I'm getting very abstract, but let's be more practical. Let's say your solution is a Fourier series expansion. So we know those are very smooth. So those are going to be k very high. Okay. Now, if you have a crack, we have a singularity, right? It turns out that k for that particular problem of the crack is 3/2. And that is the reason why our convergence rate gets degraded, right? Because if I take the minimum between p, which is, let's say, linear interpolation order 1, or k minus 1, which is in this case 1/2, well, that is what is going to control the convergence rate. You guys understand this? Yeah? So, for the p version of FEM, the problem now is that we really lost that nice property of exponential convergence. So we recover algebraic convergence as well. And beta p is going to be equal to 2k minus 1. Again, k is the regularity of the solution, and this is just for uniform meshes. Yeah, because we had a singularity, now we lost that nice property of exponential convergence, But we also saw how can we gain back that exponential convergence in those cases where the singularity is confined to these sets of measure 0. How did we manage to get that exponential convergence back? Yeah. Yes, correct. And that is, of course, what we describe as HP. And you can recover exponential convergence back. And now your theta is going to be 1 over 2d minus 1. That is your theoretical estimate for theta. And now, well, problems in category C, those are the really messed up ones. Because now we're talking about problems that have very bad behavior at some portion of your domain, right? And well, you can still get some convergence. So what you can say is that h-FEM has algebraic convergence. And you can, the only thing you can only say about this problem is that beta h is just greater than 0. Beta p is greater than 0. And algebraic convergence for that h-p-FEM, that the same applies, right? It's a combination of these two when you're doing h-FEM. But there is really not much you can do about it. So in those problems where something really bad is happening, then even going to your table and trying to find out why you're not getting convergence may be a difficult task. Okay, but let's finish just this table, and then we take a little break. Just for completeness, I want to say that D was the dimension. And K is the order of the Hilbert space U lives on, which is referred as the regularity of the solution. Yeah, so for problems in A, U belongs to HK on omega, and K is very large. So then if we look back at this table, then our convergence rate is going to be determined by the polynomial order that we're dealing with. For problems in B, on the other hand, U belongs to HK of omega, but just K is greater than 1, and in that case of the crack that we were discussing, K was in 3/2. Okay, so that's it. This is basically a summary of what you would expect to see. So in the project, for example, if you're tackling the first smooth problem, you would expect to see these rates. If you are not getting these rates, it's because really something is really wrong. Okay, but I gave you a code that was already working with h-FEM, so you should really get those rates. Okay, any questions? Okay, let's take a quick break. Let's meet in 10 minutes.